Next speaker is Jeff Greason, who I introduced earlier as one of the board members. A quarter century of experience.
And growing.
I'll let him take it from there.
Well, this is going to be my first talk for Tau Zero. I've done, John and I have tag teamed on doing rocket-related talks for a number of years now, so I could probably give your slides, but I don't think you're going to be able to give this one. It's because this is a new one. So this is a little unusual in that I'm really here to evangelize a technology that I have nothing to do with. This work is really 98% drawn on some work done by John Slow at the University of Washington. Was funded by a NIAC grant back in 2004, 2005, and as far as I can tell, it went pretty much nowhere since then. In 2009, I was on the Augustine Commission and I was doing a survey of, are there any technologies in NASA's pipeline that could really change the game in what we could do with various kinds of NASA missions? And I stumbled across this and I was like, my mind was blown. Like, you gotta be kidding. This is this close to ready and nobody's doing anything with it. But there was one problem with it, and so I kind of noodled around on it for the subsequent 8 years, and about 3 or 4 months ago, I think I solved the one problem with it, so I thought it was worth telling people about. I'm not a believer in slides where you can read everything the speaker is going to say, so I have my notes, and I just have a couple of pictures up here. But again, credit goes here to John Slow. It's his work. So I'm going to explain a little bit about how this thing is and how it works, and then I'm going to just survey a suite of missions that this enables you to do. So what the plasma magnet is a way of doing a ridiculously high thrust-to-weight magnetic sail. And I think one of the reasons that the community didn't pick this up is John Slow had an earlier idea, M2P2, of inflating a plasma by kind of feeding gas into it. And most people think that wasn't going to work. And so he went away and came up with this other way of doing it, which I can't find any reason why it won't work. And I'm pretty confident that it will work, but I think by then people confused the two ideas and didn't realize that they were two completely different things. So think for a second about an electric motor. An electric motor has a rotor and a stator. And what's going on in the stator is there's a set of coils that you energize in turn, and that makes a rotating magnetic field. And that rotating magnetic field progressively pulls on or pushes on the magnets in the rotor, whether they be electromagnets or permanent magnets, and it drags the rotor around, and that's how an electric motor works. Very little mystery there. Imagine that you have that same stator with a rotating magnetic field in it, but instead of it having a rotating rotor, you would put it in a conducting fluid, mercury, seawater, a plasma, whatever. What happens? Okay, well, there's this moving magnetic field. It tries to drag the charged particles, the charge carriers in that charged fluid along with you. In other words, it induces a current. So here it is schematically shown. You have this magnetic field that's twisting around and it drags the charge carriers around with you. What's the radius of that current that you induce? And the answer is it's only very loosely connected to the physical dimensions of the coils, because that magnetic field that you've created in that charged medium that you're in has a magnetic field pressure. And there's an equilibrium that's established that between the pressure from other sources in the thing that you're around, the gas pressure, if you're moving, the dynamic pressure, if it's magnetized, its own magnetic field pressure, and the magnetic field pressure that you generated from the magnetic fields of the stator. And what John Slow found is that the toroidal volume of current that you induce gets bigger than the coils. And that's an incredibly interesting property. If you think about using a magnetic sail, for example, in the solar wind, one of the features that has is when you're in close to the sun, the solar wind is dense, relatively speaking. I mean, still ridiculously fluffy, but denser than it's going to be later on. you get a certain magnetic field radius. You get a certain cross-sectional area that is pushed on by the solar wind. When you get farther from the sun, the dynamic pressure of the solar wind is lower, so the field gets bigger. In other words, it's a magnetic sail of constant thrust. The farther you get from the sun, the bigger the sail gets, same thrust for the same coils and same input power. So this has been tested in vacuum chambers on the ground. Seems to work. You know, if electric motors work, this is not mysterious plasma physics like a lot of things that go on where you're looking at it going, oh, gee, I don't know. I mean, I can't think of any reason why it can't work. So there are some pictures from the NIAC work. These are simulations because there's only so big of a vacuum chamber that we can test this with on the ground. But again, as this shows the evolution of the magnetic field as the surrounding magnetic field or dynamic pressure decreases, the magnetic field just keeps getting bigger. Yes?
The red button is the laser.
No, that's okay. I don't need one. So let's talk about some missions. Okay, so this is interesting. What good is it? Firstly, all high energy propulsion is fundamentally an energy problem. You know, the faster you're going, the more energy you have to consume. It has to come from somewhere. That costs money. In the case of things like beamed power for robotic-sized spacecraft to other star systems, it takes more energy than humanity produces by a fairly large factor. You know, as somebody who thinks in the commercial world, I just look at that and I see the dollar signs and I think this is not going to be happening real soon. When you're harvesting high-speed particles that come from somewhere else, you don't have to pay for the energy. You just have to pay for the energy of the field that it takes for you to interact with that charged particle stream. Depending on the conditions of the plasma you're talking about and the velocity and the size of the coils and other details like that engineers like me like to worry about, the plasma magnet gives you thrust power that's between 1,000 and 1,000,000 times higher than the power that you had to put into the coils. Now there's some caveats there. Right? If you want to accelerate, you can only accelerate in the direction that the solar wind happens to be going. So great for going out, not so good for coming in. Which leads immediately to the first interstellar problem, which is braking. Now, first I got to say, very early in the process of thinking about this, you discover that not enough is known about the interstellar medium to do confident analysis on this, which is a little bit disappointing and a little bit shocking. The Alpha Centauri is in a different cloud of interstellar gas than the one that we find ourselves in. We recently revised by a factor of 2 our estimate for what the magnetic field is in the interstellar medium that we found ourselves in. I would not put a lot of faith in estimates of what the magnetic field in the G cloud is. So the first thing you got to do is say, we don't know enough to be doing confident engineering on this. But you know, you take the numbers in the textbooks and say they're good for what they're worth. For a 2,500 kilogram class ship, that was my reference ship, thinking that leaves about 1,000 kilograms left over for payload, which is not wildly different from what the talk in JPL thought yesterday they would need for a robotic probe with real data rates and telescopes and things like that. That takes about 10, I limited myself to 10 kilowatts to feed into the system because I thought that was a credible power supply we might actually be able to package on something like that. That'll break in the interstellar medium at about 2 meters per second squared, just from pushing against the interstellar plasma. If you're coming in at half the speed of light, that takes 2 years to decelerate, and you only had to spend 10 kilowatts to do it. So this idea that we have to have 10 to the 17th joules added to the system or something like that if we're going to break suddenly goes out the window, and you start wondering, why wouldn't you stop? There's obviously a lot more useful things that you can do if you get to spend more than 2 or 3 minutes in the destination solar system. That's pretty cheap for a couple of coils of wire and 10 kilowatts. Furthermore, when you get to the destination solar system, you can then use the solar wind of the target star to maneuver, as long as you only want to go out, to maneuver out in the solar system of targets. So one can imagine, coming in, taking pictures of the destinations that you might want to go to, coming in closer to the target star, and then doing, that's not a burn, a delta V maneuver by turning the magnetic field back on long enough to pick up velocity in the desired direction to do an orbit around the target planet. I thought there'd be a clock in this room, so I'm flying a little blind. 15 minutes, okay. Closer to home, it's obviously useful for things like the 1,000 AU or focal missions. And I want to say, I know there's going to be a lot more talk about solar gravitational lens focused missions tomorrow, but the most obvious thing about the gravitational lens missions is you need a lot of them. You know, the nature of the gravitational solar lens is it's a lens. If you want to look at Alpha Centauri, you've got to be on the other side of the sun from Alpha Centauri. If you want to look at a different star, you have to be on the other side of the sun from that star. So, you know, it's not like you're going, if we do start doing gravitational lens missions, it's not like we're going to do one. We're going to do as many of them as we have things that we want to look at. So they better be cheap to get out there. Okay, now take that same system we talked about, 10 kilowatts of coils and a 2,500 kilogram spacecraft. It accelerates in the solar wind at about half a G. That takes about half a day to get up to solar wind speed, which is, depending on which direction you're going, 400 to 700 kilometers per second. That is way beyond the reach of any currently existing propulsion technology. That takes about 5 years to get to 750 AU, which is great for interstellar medium exploration. It makes things like the focal mission practical. And you're talking about a spacecraft that you can launch on the smallest Atlas V that would get out to focal in 5 years, which makes, to me, all kinds of interesting. Just in case you don't know, solar wind is not as simple as you might think. It's stirred around by the sun's magnetic field in the equatorial plane in interesting directions. It's a lot faster over the polar regions than it is in the equator and the plane of the ecliptic where we're at. But the important thing is it's there in every direction that you'd want to go, and it's always, by chemical propulsion standards, blindingly fast. So coming even a little closer to home, the problem with this for use in the solar system is how the heck do you stop? And that's why when I came across this night 8 years ago, I was like, great, it'll get you to Mars in a week, but only if you went to wave going past, because it's too good for its own good. We don't have a way of stopping for 400 kilometers per second today. You know, there's no chemical rocket system in the world, and Mars isn't even close to big enough to stop. I mean, you'd have to crash. There's no other way to grab onto Mars to stop from 400 kilometers per second. Its gravitation is not even, or atmosphere is not big enough to think about it. There's one body in the solar system that's got a big enough magnetosphere to stop in, which is Neptune. The Neptune, for whatever reason, has an anomalously large magnetosphere. And so if you stop it, if you crank up the coil power to stop at 5 Gs, you can get up to 400 kilometers per second and just barely slow down to Neptune capture speed in the magnetosphere of Neptune, which gets you to Neptune in 4 months, if that's of interest to anybody. But Mars is where NASA really wants to go. And I couldn't think of any way to do that. And that's the one original contribution that I'm making today, which is I found a way to stop. It comes from the interstellar braking idea. You know, where did the high-speed plasma come from in the interstellar plasma that you're braking against? It's not the solar wind. Well, the answer is it came from a change of reference frame. The interstellar plasma is normally thought of as stationary, but if you have this spacecraft that's moving at tremendous speed, it's moving at high speed relative to the interstellar medium. If there were a stream of charged particles that were at rest with respect to Mars that you were flying through, you would be going at 400 kilometers with respect to those charged particles. They would have a very high effective specific impulse because your delta V to the particle stream would be very high. And unlike most charged particle propulsion systems here, you don't have to pay for the energy to get them up to very high speed. You just have to pay for the energy for them to escape Mars in the direction of the spacecraft. Now you need a source of all that mass. You know, if you're slowing down, Mars missions tend to be bigger. So let me take a reference spacecraft of 100,000 kilograms. If you're trying to slow down a 100,000 kilogram spacecraft, you need something on the rough order of 100,000 kilograms of stuff to run into. That has to come from somewhere. The obvious place to get it from is Phobos or Deimos. They're conveniently in Mars orbit. They're most of the way to Mars escape already, and you may think of them as small bodies, but you can dig 100,000 kilograms out of Phobos a lot of times before you start to notice. They're only small in cosmic terms. And the energy to do that, to slow down a spacecraft at a couple hundred kilometers per second coming into Mars orbit that way, it takes megawatts. Now, you had to pay to get the multi-megawatt solar plant and the particle launcher to Phobos the old-fashioned way, by paying John or somebody like that to do that. But once you've done that, it takes half a day to accelerate and about 4 days to reach Mars orbit and about 2 days to slow down. So that gets a manned spacecraft to Mars in about a week, which I'd like to think somebody would be interested in. The step that's left is to fly one of these things. As far as I can tell, if you get ahead of me the project and say, what would you do next? I'd say I'd fly something, because more ground testing, they've already put it in the vacuum chamber and measured the thrust, but I'm not sure what more testing to do on the ground. So at Tau Zero, one of the projects we have in our portfolio is I'm trying to do just enough scoping to see if I can figure out how to do this with like a 100-kilogram ride-share payload. The drawback being it has to be a ride-share on something that's going to the moon or to Earth, or otherwise to Earth escape, because you have to get outside the magnetosphere of the Earth before you turn the device on, otherwise there's no solar wind to interact with. So you got to get at least pretty close to the orbit of the moon if you're on the sunward side of the Earth before you can get into the solar wind. By no means is that mission design done, but I think it's doable, and that would give kind of a 100-kilogram class mission that we could do some incredibly interesting technology development work with. How am I doing on time?
You have 10 minutes.
Ooh, rockin'. Well, in that case, I've got a few more teasers to throw out. So you can get to Mars in a week, but how the hell do you get back? One of the advantages of going to Mars quickly is that you don't fry from cosmic radiation on the way. Now, personally, I think if you could get to Mars in a week, many more people would go to Mars than would ever come back. But they still have the problem of getting back. The classical answer to that is, of course, the Aldrin cycler. You have a big, heavy habitat that is in orbit, in a repeating orbit, such that it does a close pass through Mars and a close pass by Earth on every trip. Normally, you think of needing many of these things, and the reason is twofold. Number one is you have the fast path, well, the trip outward happens on a different cycle than the trip inward. So if you want to make round trips, you got to have one habitat for going out and one habitat for going back. That's the best news. The worst news is Earth turns out not to have enough gravity to turn the Aldrin cycler around without using propellant. You're like a little less than a kilometer per second short. And for a massive habitat, that's a big, expensive maneuver to do. If you're talking about something, like a cosmic ray shielded space station, you're talking about an impractical amount of propellant. So if only there were some propellantless way to get a kilometer per second of delta V going away from the sun every time that you passed by the Earth, the Aldrin cycler would work. This is one. It doesn't take much in the way of power and coils to grab only a kilometer per second out of a 400 kilometer per second wind. So you turn the coils on every time you swing by the Earth, you add your extra kilometer per second that you were missing, now the Aldrin cycler works. And if we can get to Mars in a week going outbound, we really only have to worry about coming in. You don't need the outbound Aldrin cycler anymore for radiation shielding, so that gets you down to one, which starts looking credible. And we talked about the demonstration mission. Okay, 2 words on interstellar stuff. This by itself totally opens interstellar precursor missions, but it of course doesn't get you to other stars, because even 700 kilometers per second is only about 2% of the speed of light, 0.2% of the speed of light. But there are 2 interesting ways of using this technology for real, hair on your chest interstellar missions. One is you can use it as a target for particle beams instead of for laser beams. Particle beams carry a lot more momentum than laser beams do. In very round figures, you need about 1% of the power in a particle beam that you would need in a laser to get the same job done. If you had a particle beam and you wanted to shoot the canonical 2,500 kilogram payload to about 20% of the speed of light, you'd need about a terawatt. A terawatt is still a lot of power. It's about as much as India uses, but it is an amount of power that is technologically within the capacity of the human species to think about using. The problem with particle beams is twofold. Well, the problem with all beams is your target gets hot, and that limits how much acceleration you can put into the widget. The problem with particle beams specifically is they don't collimate as well as lasers. You know, it's very hard technologically to do a very tightly collimated particle beam. The Mars particle beam I talked about previously for stopping at Mars, we only need about the collimation we've already know we can do in particle beams has been demonstrated. And the reason for that is that the magnetic field of the approaching ship is rather large. When you're coming into Mars, the magnetic field is about 100,000 kilometers in radius, which gives you a big target to shoot at. But yeah, on interstellar distances, even that isn't enough. So you would need a revolutionary improvement in the collimation of particle beams. I've looked at that a little bit, and there's no law of physics that says that that can't be done. What you have to do is launch dust grains rather than launching individual charged particles so you can overcome the space charge limitation. Technologically difficult, not a law of physics problem. And of course, magnetic fields do not melt. So there's no particular problem with sail temperature if you're shooting at a magnetic field instead of shooting at a physical sail. So you can actually imagine pouring the terawatt into the thing for that, months that it would take to get up to 20% of the speed of light. The last one, which is a talk I thought I might give this year, but it looks like I'll save it for a future year because the scheduling didn't work, is you can use this same trick. You can use the magnetic sail to get up to 700 kilometers per second. And instead of launching inert mass or particles, you can launch fusion fuel pellets. And if you run fusion fuel pellets into a target at 700 kilometers per second, you are well on your way to lighting them off as a fusion reaction. Some quick back-of-the-envelope numbers suggest that using that kind of an approach, you can get a man-sized 100,000 kilogram spacecraft up to about 20% of the speed of light, with only using about 10% of the lithium production that humanity currently produces to make lithium-6 deuteride pellets to shoot. So it kind of looks like there's a pony there, but we'll save more details of that for a future year. And with that, I'll take questions, because it looks like I'm down to 5 minutes.
Can you clarify a couple of points? One is that you started off saying that the magnetic sail was efficient or useful in cases where there is a flux of particles, solar wind. And then you started to say it was useful in areas where there are magnetic fields. This is effective in both areas. Is that correct?
Okay.
Or in both situations?
The plasma magnet is really just a magnetic sail of phenomenally large dimension for phenomenally low weight. Because instead of having to carry the giant loop of wire, you're making the charged medium, be your loop of wire for you. But like a magnetic sail, it is fundamentally a drag device. So it's useful. If there happens to be a wind blowing your way, you can acquire the velocity of that wind. If you happen to be moving and you through a stationary cloud of something and you'd like to slow down, it's useful for that. But it is not a caterpillar. It doesn't start from a standing start.
So it is fundamentally a particle-based
Yes.
interaction, not
Yes.
a magnetic field or plasma magnetic field interaction.
Well, the plasma magnetic field interaction is used to synthesize the circular current,
yeah.
but then once you have the current, yes, you're fundamentally interacting with the particle momentum flux that you're passing through.
Okay, thank you.
Okay, Greg Matloff again. I think you're being a little pessimistic in talking about your applications of this approach to interstellar spacecraft carrying humans. Because if world ships do grow out of O'Neill-style space habitats, there's no reason why they couldn't sustain multi-millennial trips between the stars. And in a case like that, you really have something.
Peace. If you're willing to take 3,000 years to get to the next star, you could leave next Tuesday.
Yeah.
That's a philosophical thing. I don't find myself thinking about that kind of application because I can't think of how to fund it.
And that's because also you live on a planet. If you had lived all your life in a space habitat, so what?
You're absolutely right.
Yeah. Okay, thanks.
Doug Loss, have you given any thought to the possibility of scaling this down so it might apply to the breakthrough starshot, Star Wisp, for course correction and maybe even decel at Proxima Centauri?
I've been thinking about that just today. I'm not optimistic. The scaling of magnetic fields and power supplies to drive them down to gram scale has some serious scaling challenges. I used to be in the chip business, and there's a reason why you don't find inductors on chips. So on the other hand, without taking that particular project and just saying, could you imagine scaling down to, okay, if you wanted to tackle that kind of problem, what you would be tempted to do is say, can we do something intermediate? Can we scale to like a kilogram target instead of a gram? And then you'd be talking about like a gigawatt particle beam to push it instead of a terawatt. And then you could push it with the particle beam instead of the laser, and then it would be able to slow down when you got to the target. And a radioisotope power source that doesn't take up all of your payload at a kilogram might actually be credible. So there might be a way to do a small thing without necessarily doing that particular small thing.
Okay, thank you.
Okay, on to the next speaker.
Thank you all.